Hello, so it's 10:30, we are going to start. So it's my pleasure to introduce to you David Nesvorny, who is an invited professor by the Assembly of Professors of Collège de France. So David Nesvorny is a great expert in solar system formation and history of evolution, but he has also worked extensively on various problems about extrasolar planet dynamics. So David is originally from the Czech Republic, so he did his undergraduate studies in Prague, and then he moved to Brazil for the PhD to work with a famous dynamicist, Silvio Ferraz-Mello, the University of São Paulo. And after the PhD, he came to Nice as a postdoc, working with me, then came back to Brazil to work for a couple of years, then came back to Nice to work for another year as a postdoc, and finally got a position as a researcher at the Southwest Research Institute in Boulder, Colorado, where he's still there today. And he did another sabbatical in Nice and so on. So we are long-term collaborators. So David is really a great expert on all the steps of solar system formation and evolution. He has modeled planetesimal formation, and this is what we are hearing today, but he has also modeled the evolution of the giant planets during the instability, the breakup of asteroid families in the asteroid belt, their relationship with dust. He modeled the zodiacal cloud, he modeled the origin of meteorites. He's now modeling terrestrial planet formation, so always with great detail. He's a great expert, so it's really my pleasure to invite him here, and he will give a series of 4 lectures, bringing to you the latest results. So today about planetesimal formation and formation of binaries in the Kuiper Belt, and presumably also in the asteroid belt, but even if we lost those. Then next week, it will be about the origin of comets, of their reservoirs. Then on asteroid families as sources of near-Earth asteroids and meteorites. And finally on near-Earth asteroids as modeled is also done the most accurate model of the near-Earth asteroid distribution. So apparently, as an invited professor from Collège de France, you deserve a medal. Wow. So I didn't know. So this is the medal that the Collège de France offers to you,
very much
for this series of lectures. And so I give the floor to David. Because the lecture is recorded, I think it's better if we collect all the answers at the end. But this time, unlike the official lectures in the main room, we do have time for questions after the talk, and so don't hesitate to ask. So David, the floor is yours.
Thank you. I'm really happy to be here at this beautiful place. Thank you for coming. I hope you will be entertained and you will learn a few things as well. So, as Alessandro said, today we will talk about planetesimal formation, which is an important step towards planet formation, right? Planetesimals are the first small planets that form and then have to accrete more mass to become full-size planets. And I will try to explain how observations of Kuiper Belt binaries help us to understand these early stages of planet formation. So to start with, I will invite you on a trip on an alien spaceship that's just approaching the solar system from the interstellar space. Of course, if you would be on that spaceship, you wouldn't see much with your naked eyes, right? But let's assume that the aliens have powerful telescopes and they can see almost any small object there is. Also, this is accelerated movie, right? The best thing to think about it is like a time-lapse movie, where you take a picture once a year and then you condense it into a very short animation. There are computers on board of that spaceship that computed the orbit of any small body there is, and the computers are probably testing different models of the formation and evolution of the system because of the small body distribution is an important clue to how planetary systems form and how they evolve. So, of course, the main interest in the system is the third planet from the Sun. We measure the distances in the solar system by using a stick which we call the astronomical unit, which is the mean distance between the Sun and the Earth, about 150 million kilometers. On your right, you see the two structures that the aliens could have seen. It is a flat belt of small bodies just beyond the orbit of Neptune that we call the Kuiper Belt. It is about 100 astronomical units across. And then at much larger distance from the Sun, there is a more spherical structure of bodies that we call the Oort cloud. And that's the source of long periodic comets. So the Oort cloud will be the subject of the lecture next week on Thursday. And today we will talk more about the Kuiper Belt. So I would like you to think about the Kuiper Belt as a fossil of the formation and evolution of the solar system. In much the same way that the Lucy fossil helps the anthropologists to understand the evolution of human race, the Kuiper Belt helps us to understand the formation and evolution of the giant planets. So today we know more than 3,000 Kuiper Belt objects. This will soon change because of the Vera Rubin Observatory is entering operations in Chile. And it is estimated that we will know about 15,000 KBOs within a few years. So that will be a true revolution. And we will learn a lot of new things about the Kuiper Belt. But for the moment, let's work with what we have. The sizes of these objects range from the smallest, 10 kilometers across. We don't know many of those. To the dwarf planets like Pluto or Eris that are almost 2,500 kilometers across. So there is a great diversity of sizes in the Kuiper Belt. And most of the objects that we know of are sort of 100 kilometers in size. So I said that the Kuiper Belt provides important clues to planet formation. So what are these clues in the first place, right? And the first one comes from unexpected observation that the Kuiper Belt objects are often found in gravitationally bound pairs. These are two objects that feel each other gravity, and they go around an orbit around each other. We call these binaries, and on the left side, you have an example of observation of the Mars-Somnus binary by the Gemini telescope. So if you look at that picture, you immediately see one thing, that the brightness of the two components is about the same. And that tells you that the two components of the binaries have about the same size. In this case, for Mars-Somnus, it is estimated that the two components are about 60 kilometers across, and they are separated just over 20,000 kilometers. So to give you a sense of the size of components relative to their separation, I scaled down the binary to the size of tennis balls. So instead of 60 kilometers, you have 6 centimeters. Instead of 21,000 kilometers, you have 21 meters, and that's the size of a tennis court. So as you can see, there is plenty of space between the two components, right? And that's the reason why we call these binaries widely separated binaries. This is rather a typical binary. There are some binaries that they are separated 5 times the distance, 5 tennis courts, which would be a football field, 2 tennis balls at the opposite sides of a football field. Those are extremely separated, but they are just a few of them, so they are not the main focus of this talk. On the other hand, when the two components are separated less than a few tens of thousands of kilometers, even with the best telescopes we have, it's difficult to resolve them, right? Because on the sky, they have a separation that's small fraction of the arcsecond, and then even Gemini or Hubble space is unable to resolve them. So we are blind to binaries that are tighter than this. And the population of binaries might be much larger than what we actually see. If you would look through a telescope, this binary, we would see the two components going around each other. You would see them closing the loop in 961 days, which is the orbital period of this binary. And from that, you could calculate the mass, the total mass, using the Kepler law. And because of you have estimate of the sizes of the components, this gives you a density. And that density usually comes to be very low, roughly 500 kilograms per cubic meter, which is half the density of water, which tells you that, well, there must be a lot of porosity in these bodies. They didn't melt. If they would melt, there would be no porosity, but they probably formed late in the evolution so that aluminum-26 didn't heat them enough to reduce the porosity, right? So these are porous objects that probably formed late in the evolution of the protosolar gas disk. Also, the orbital speed is only 6 kilometers per hour. That's a walking speed. You would be able to walk with one of the components. And that's very unusual because in the solar system, the speeds are measured in kilometers per second. For example, the Earth is going around the sun at 30 kilometers per second, right? So this is an extremely low speed. And this is significant because if you imagine that, during the evolution of the solar system, there is some perturbation, like a small impact on one of the components. It can easily change the velocity by this amount, right? And if it does, then the components become unbound, the binary dissolves, and we wouldn't have these binaries in the first place. So this tells you that the binaries are extremely fragile. They are fragile. And for that, to survive, they have to be located at a special place at large distance from the sun. And this also explains why we don't see these binaries in the asteroid belt. In the asteroid belt, you have so many collisions happening that they just dissolve, right? The probability of survival in the asteroid belt is 0 for these binaries. So that's why the Kuiper Belt is important. That's the place where these binaries can survive. So far we had that these binaries are similar size or equal size. They are widely separated. They are fragile. And the fourth property of these binaries is that there are a lot of them in the Kuiper Belt. There are populations, subpopulations of the Kuiper Belt that we call the cold classicals. That population is thought to be the most pristine, the one that survived. It had low eccentricity, low inclination. It's 45 astronomical units from the sun. And in that population, the binary fraction is at least 30%. So 1 in 3 objects you look at is a binary. That's surprisingly high, right? And we don't know the tight binaries. So if the population of the tight binaries is substantial, then potentially, almost every object in that subpopulation is a binary. So before I proceed, just a reminder about the orbital elements. There are 6 orbital elements. 3 orbital elements are the most important. That's the semi-major axis that measures the size of the orbit. Then we have eccentricity, which measures the elongation of the orbit. So planetary orbits, for example, are pretty close to circular. They have low eccentricities, eccentricity close to 0. But cometary orbits, on the other hand, they have very elongated orbits and eccentricities that can be close to 1, right? And the third element I will be using is the inclination. Inclination is typically measured with respect to the plane of the solar system or the ecliptic. Again, planets have low inclinations. Some comets can have very high inclination polar orbits with inclination 90 degrees, or even retrograde orbits with inclination larger than 90 degrees. And then the perihelion distance is the closest point that the body reaches along its orbit to the sun, and that's a simple function of the semi-major axis and eccentricity at the bottom. One more clarification is that there are always two orbits involved because we are talking about the binary, right? So the first one is the big orbit. That's how the center, the body center of the binary moves around the sun. That's the large orbit. It's measured in astronomical units, and it's typically 40, 50 AU in this case. And then there is the small orbit. That's the binary orbit, which we call the mutual or binary orbit. That semi-major axis of that for Mars Somnus we have seen is something like 20,000 kilometers. That's the small one. So sometimes I forget to clarify which orbit I mean, but I'll try to be careful about it. But also you, when you think about the thing, the arguments involved in this, think which orbit it is, right? Be careful about not confusing the orbits. So when we look at these orbits, these are the small orbits. These are not the heliocentric orbits of the binary. These are the mutual or binary orbits, right? And they look a little bit strange because there is no massive object in the middle and a small satellite running around it. Because of the two bodies are similar in mass, they both orbit around the common body center, which is the cross in the middle. That's a little bit unfamiliar situation here, but that's the nature of it. So we have four properties: equal size, wide separation, there are a lot of binaries, and they are fragile. Okay? So how these primaries form in the first place? So there has been at least two models suggested for the formation of these binaries. One is capture, and the second one is co-accretion. So the idea of capture is that you have two bodies that form at different locations, maybe even at different times, and later on, still early in the evolution of the solar system, but later on, they have a close flyby, and something causes them to be caught on a bound orbit. And that something can be a collision, when a small body impacts on one of the components, induces a change of the velocity, and just by randomly affecting the speed of this component, it leads to a capture. It can happen, right? It doesn't seem to be a very efficient mechanism to producing binaries, but it can happen. The other possibility for a capture is an exchange reaction. That doesn't involve collision, but you have, again, flyby of two massive bodies. There's a third body involved. That body gains kinetic energy. These two lose it, and they end up on a bound orbit around each other. So that's capture. The second possibility is co-accretion. Co-accretion is a different kind of model. It assumes maybe there was like a cloud of particles and larger objects that just collapsed when the planetesimals formed. And if there was some rotation to the cloud, maybe instead of forming a single object, you can form some sort of a bound pair or more complex triple system that later evolves, right? So these were the two ideas, capture or co-accretion. And now, how do we know which one applies for the observed Kuiper Belt binaries? Well, one of the important inputs to this is composition. So from the James Webb Space Telescope and from other observations, we know that the Kuiper Belt is a compositionally diverse population. They are bodies that are rich in water ice. They are bodies that are CO2, CO rich. And they are bodies with complex organics on the surface. So this sequence is thought to represent the temperature gradient in the protosolar nebula, or radial gradient, where maybe these water-rich bodies formed on inside, maybe 20, 30 AU from the sun, the CO2, CO rich in the middle, maybe 30, 35 astronomical units from the sun, and then the bodies rich in organics at maybe 45 AU. It's not very clear where these boundaries are, but that's the general idea. The problem with this is that today, the composition is not correlated with orbit. So if you look at the body at 30 AU from the sun, it will not necessarily be CO2, CO rich. There was a lot of mixing happening in the early evolution of the solar system, so that we don't have this correlation. And this suggests the dynamical mixing of this population. So what that means, right? If the capture model applies, then you have two bodies that form at different locations. Maybe they would have different composition. So when they are captured and form a binary, then you would expect they would have different composition and different spectra. In co-accretion, on the other hand, you have these bodies forming from the same material, right? So they would have the same composition, same spectra. So which one is the case? Well, it turns out that the binaries, the two components in a binary, have the same composition. This is an example, again, for the more sumless binary. This is a JWST spectra, and if you compare this with this, you see that they are nearly the same. We have additional JWST spectra from other binaries, and we also know from previous color observations that also the binaries have matching colors. If you look at Kuiper Belt can have very diverse colors, but if you look at the two components of the same binary, those two components have matching colors, and therefore matching composition. So this is a very strong argument against capture and in favor of co-accretion. It's really difficult to imagine how capture could produce this thing that the two binary components know each other composition in some sense. Okay, so we will consider co-accretion. Now, if you go to protoplanetary disks and you understand that there is a very complex physics involved. You have sublimation lines where different species can condense and particles can grow. You have turbulence. There are magnetic fields, irradiation, both from the central star and from outside. So there are researchers that spend their whole lives researching just maybe one component of this complex protoplanetary disk. But fortunately for us, we don't have to care about all the complexities. We can just consider the outer part of the disk, maybe at 40, 50 AU, where Kuiper Belt bodies are at the present time, and consider just two components of that gas disk. On one hand, you have the H2O gas, molecular hydrogen gas. At these large distances, the disk is pretty puffed up vertically because of the solar irradiation. And then you have solid particles in the disk that first condense. When they condense, they are tiny. But then by mutual collisions, they can grow to something maybe millimeter, maybe centimeter size. So you have all range of sizes of these particles. And the particles, they settle towards the midplane of the disk here, just because of the vertical component of the solar gravity. They settle to a disk that's much narrower vertically than the gas disk. Now, there are all sorts of particles, but for us, the most important particles will be of certain size, which may be like millimeter to centimeter size in the Kuiper Belt, that we will call pebbles. Now, pebbles, or the astrophysical pebbles, they have an exact definition based on the Stokes number. which defines their interaction with the gas disk. So the Stokes number is simply defined as a ratio of the stopping time over the orbital period. So it's a normalized stopping time. And the stopping time is essentially if you have pebble that's moving relative to the gas, how long it takes for the pebble to adopt the gas speed to be essentially not moving in the frame of the gas, right? How long it takes. So these pebbles are special because of if you have small particles that are perfectly coupled to the gas disk and have stopping times much lower than 0.01, then those particles just follow whatever gas is doing, right? Just follow. And nothing interesting happens for them. They don't grow, they don't produce planetesimals or something, right? So the small particles are not significant. The large particles, which have Stokes numbers much larger than 1, maybe 10 meters, maybe 100 meters, they also don't do anything interesting because of they just ignore gas, basically, right? So that's why this intermediate regime of Stokes numbers between 0.01 and 1 is the most interesting one. So let's consider how these pebbles behave in the gas disk. So you have the protoplanetary gas disk, and this is just a 3D box somewhere in the outer part of the disk. Direction to the star is to the left, sense of orbital motion is up, and you also have the vertical, it's a 3D box, it's not just a 2D box, right? And let's first consider a single pebble. So single pebble is going at its Keplerian speed, right, around the sun, or wants to go at its Keplerian speed around the sun, but the gas is going slightly slower. The gas is pressure supported. And therefore, the pressure compensates for a tiny part of the solar gravitation, and the Keplerian orbit for gas proceeds at slowly lower speed than that of the pebble. So this leads to a situation that the pebble feels a headwind. The headwind extracts the orbital energy, and then the particle will be moving radially towards the sun. So that's the basic interaction, right? And this motion depends on the Stokes number. Can be fast, can be slow, can be intermediate. Now, if you consider an agglomeration or concentration of pebbles, that behaves slightly differently, right? Again, the pebbles want to go at their Keplerian speed, but they start dragging the gas with them. They start to be significant. Not only they are affected by gas, but they start being affecting the gas as well. So if that happens, they will feel a smaller headwind and will go slowlier. They will have slower radial drift. In some sense, this is similar to, to the France race, where you have a single rider in front of the peloton, and it feels a stronger air drag. And the peloton riders, they are dragging the gas with them or the air with them, and they have easier time to go. And in this situation, it's likely that the single rider will be caught by the peloton. Peloton increases in size, right? So that's related to the peloton effect. But the real instability that happens in the gas disk with pebbles is much more complex than the peloton effect. To start with is 2D. Not 1D. The Tour de France riders are essentially moving along the road in 1D, but here we have 2 dimensions, right? But there are many important differences as well. So don't be fooled, it's not just a peloton effect, but it relates to it. So what happens in the real situation, and we call this the streaming instability, is that the pebble concentrations will move at different speed than individual pebbles, and they will get more and more pebbles over time. And that's the first step towards the formation of planetesimals. You agglomerate pebbles, and then you hope later that they will collapse in solid objects, and I will show that in detail. Now, the streaming instability regime depends The streaming instability not always works. It needs the right condition to work in a disk. One condition I already mentioned, right? So in this plot, you have the Stokes number here in logarithmic scale, and the solid abundance relative to the gas abundance. It's just the column density ratio. And the place where the streaming instability is the most efficient is this green area on the top of the plot. So one of the conditions I already mentioned, right? The Stokes number needs to be between 0.01 and 1 in this region, roughly, for the strong and rapid clumping by the streaming instability to happen. The second condition is that the solid abundance has to be significant. If you have just 1 or 2 pebbles in a gas disk, nothing happens. You need to have a lot of them for them to start to affect the gas, and that's when the streaming instability can kick in. There are also other conditions, but these conditions are not too restrictive. It's not like a little niche of initial conditions or the physical conditions in the disk that the streaming instability would work. They are quite reasonable. For these kind of pebbles and this density, you get the streaming instability. And so the point is that the streaming instability can work in lots of different situations. So after all this, let's assume that we have the conditions in which the streaming instability works, and let's consider numerical simulation of the streaming instability. So here you have again the same patch of the disk. It's a 3D box, and this will show an animation that's coming from a hydrocode, which is quite sophisticated hydrocode that accounts for the gas in this box. There are about 1,000 grid cells in each direction, 1 billion cells in total. They are about 150 million particles inside of this box, so it's a large number. And the simulation accounts for 2 effects. For the aerodynamic gas drag on pebbles, and pebbles can back react and drag the gas with them. So there is both reaction and back reaction in the simulation accounted. And what you see here is the pebble density. The gas is ignored. You don't see the gas. You see what the pebbles are doing. So this is what happens in the simulation. And these are the 3 stages going from left to right. So at the beginning, you have these azimuthal filaments. Remember that the sense of motion is up and the sun is to the left, right? So you have these azimuthal filaments that start forming and start moving. Then, when the filaments become dense enough, they will fragment into individual clumps. And then, by the end of the simulation, you have hundreds of clumps. These are not planetesimals. These are just big clumps of pebbles that are gravitationally bound to each other. The circles are kind of like the reach of the pebble cloud gravity. And the fact that the pebbles are inside this Hill sphere means that they are gravitationally bound. So that's nice. From almost uniform distribution of pebbles at the beginning, we get these clumps. But now what, right? The problem with this simulation is that is the gravity code. The gravity code, to be able to deal with 150 million particles, you need a very fast code. You cannot do full n-body. So this is a Fourier-based grid gravity code that is excellent, but when the concentration reaches the size of the grid, the code basically fails. It won't show you how these clumps collapse on each other. So for that, you need to switch to something else. This hydrocode will not show you that. So what people do is that they take, from the previous simulation, they take one cloud at a time and ignore everything else. And that can be done because the collapse time of each individual clump is much, much, much faster than the interaction between different clumps. So you can ignore the interaction, essentially. You can consider one clump at a time. And then you have to plug it in a different code that's capable of dealing with whatever scale of gravitational interaction there is. This is a PKD graph code, which is a tree-based gravity code, which can deal with kind of like million particles is max for that code. In that code, you can already forget about gas, because the density of solids in this box is orders of magnitude higher than the gas. So the gas at this point is insignificant. It was important for the streaming instability to start, but now it's unimportant. You need to account for collisions between pebbles in the simulation, right? Because of the collisions will create larger objects. If you ignore collisions, you don't get planetesimals. You need the accretion to happen. But even more fundamentally, the collisions are important because of they are inelastic and they remove the kinetic energy from the cloud. If you wouldn't have inelastic collisions, the clump would behave like an elliptic galaxy, where stars do not collide and the elliptic galaxy doesn't collapse, right? So this is accounted in this code, and this is how it looks like when you look from distance. So this box is about 100,000 kilometers, even more, I would say a few 100,000 kilometers across. And this is how it looks like if you look from close. So I just zoomed in to see what's happening in the middle. And this part of the simulation, I repeat it a few times so that you see the initial collapse. This is slightly more accelerated so you can see the final result as well. And you can see the binary forming in the middle. So again, there are a few stages to this evolution of the collapse. You have the initial collapse where the inelastic collision happen, remove the kinetic energy, everything starts collapsing. Then typically you have this stage, which is a dense disk forms in the middle. Then there is an infall of the material which brings high angular momentum. That's the infall on the disk. So the disk becomes unstable at some point and shreds, right? But if you wait long enough, you always find that there is a binary, almost always find that there is a binary forming in the end. That's basically because of there is always some random rotation in the clump, right? And because of you need to preserve the angular momentum, you form a binary. You cannot form a single object because of that single object would be rotating too fast and would fission, right? You also don't form like an unequal sized binary where you have big primary and small satellite because of that satellite doesn't include enough angular momentum. So forming the equal sized binary is a natural product of the initial rotation in these simulations. Now, this is just one case, right? But how do you compare the model to observations? Well, you need to repeat this many, many times to build up statistics in the model. There are lots of different clumps, larger ones, the ones that rotate more, smaller ones, the ones that don't rotate, right? So you go through the simulations, you repeat this many times to build statistics in the model. And once you have that, you have population of binaries that you can compare to the population of observed binaries. And that's what researchers do. This is an example of the simulations that have been done. I would like to just look at this highlighted column that shows the radius ratio of the components, R2 over R1. R2 is secondary, the smaller component. R1 is the primary, the larger one. And as you can see, in most cases, the ratio is larger than 0.5. So the components are within a factor of 2 in size comparable to each other. So these are similar size components, not exactly equal, but the observed binaries are also not exactly equal size components. They are similar size components. So that matches. And in fact, if you compare this in detail, it matches very nicely the observations. The 3 dots here mean that binary didn't form in these simulations. There was not enough rotation. So in most cases, you form equal size binaries, but in some fraction of cases, you form a single object just because of the cloud wasn't rotating enough. And that also matches observations, because if you get lots of binaries, and we know that there are lots of binaries in the Kuiper Belt, right? So this works quite well. What else can we compare? Well, we can compare the orbital inclinations of the binaries. And now we have to be careful which orbit are we talking about, the big one or the small one? Well, we are talking about the small orbit of the binary orbit and how it is inclined relative to the solar system plane, right? So the angle, so these are all the observed binaries. They are color-coded depending on which population in the Kuiper Belt they belong. This is the same major axis of the binary, and this extent is the pericenter to apocenter. That expresses what the eccentricity is of each binary. But what's important here is the inclination. So this is a polar plot, and the inclination is given in degrees with respect to the negative x-axis. So this, for example, has 10 degrees, and here we go, right? So what you can see is an interesting observation here. Most of the binaries are prograde. They orbit in the same sense as planets around the sun. And a few binaries are retrograde. They orbit in the opposite sense. So we can ask the question, if you have this model, we build up the statistics in the model, does it fit this or not? So just a reminder, 80% prograde, 20% retrograde, so there's 4-to-1 ratio between the two. Well, it turns out that the model fits this distribution beautifully. This is a comparison. The binary inclination is on the x-axis, so you have the prograde binaries here, retrograde binaries here, and this is a cumulative number, normalized. So to read this figure, for example, if you are at 90 degrees, then you see that 80%, and you look maybe at the observations, which is the red line, you see that 80%, roughly 80% of binaries have inclinations lower than 90 degrees. They are prograde, right? Which was the same thing we saw in the previous plot. And now the blue is what we get from the model. The gray is just statistical uncertainty. So one can see that there is a pretty good agreement between the model and observations. There are lots of wiggles because of just statistics. We know only like 50 binaries in the Kuiper Belt that have inclinations determined. We know many more than that, but you have to monitor the orbit for a long time to get the inclination. But there is this beautiful agreement, and the uniform distribution would like this, right? Would be 50-50 split between the prograde and retrograde, which is distinct from that. So this is, in addition to everything else I have already said, a really strong argument that the binaries in the Kuiper Belt really formed by this mechanism, by the streaming instability followed by gravitational collapse. So these are some of the successes of the streaming instability model: the matching composition, the inclination distribution, the high binary yield. I've shown that the streaming instability and gravitational collapse produces a lot of binaries. And I didn't talk much about the separation, which is another parameter you can compare, but that fits nicely as well. So, but it turns out that the wide binaries in the Kuiper Belt are not the only constraint on planetesimal formation we have. Another constraint comes from the flyby of the New Horizons spacecraft by a small Kuiper Belt object that we call Arrokoth. That flyby happened in on January 1st, 2019, I believe. And this is the picture that the spacecraft has taken. It's pretty spectacular, right? It turns out that the Arrokoth is a contact binary with essentially two bodies that are attached to each other by this narrow neck. So if we have a model for planetesimal formation, it has to account for the formation of contact binaries as well, right? Because of the only object that was imaged from close by is a contact binary. Maybe it's special, but I would expect that there will be lots of contact binaries in the Kuiper Belt as well, right? So that's one constraint. Second interesting observation is that the large lobe of Arrokoth, that we call Venu, is kind of like a pancake. Its dimensions are roughly 20 times 20 times 10 kilometers. So it's an oblate spheroid with the 2-to-1 axial ratio. It's flat. This is the long axis, and this would be the short axis. So this probably relates to some rotation during the formation. Because of the more rotation you have, you probably produce more oblate objects. The third interesting observation is that there are these mounds or little mountains on the surface, right? So there was some geological mapping done on this, and that mapping revealed that there are a dozen large mounds on the surface, and they have characteristic size about 5 kilometers. So nobody knows what these mounds are. People suggested maybe sublimation over the edge of the solar system can depress the surface in certain ways, but there are no detailed models about it. So, but it's possible that some physical process produced this depressions, but also it is possible that somehow it relates to the formation of Arrokoth. Maybe these 5-kilometer mounds represent the building blocks from which Arrokoth formed, which then come together, smashed on each other, and somehow it relates to planetesimal formation. So these are the three features: contact binary, flat, large lobe, and the mounds. So what do we do about it? So given what I said, people interpret these features in terms, again, of the streaming instability and gravitational collapse. So again, you have the streaming instability kicking in, producing a cloud. From the cloud, you form a binary. But you expect to form a binary that's detached, not a contact binary, right? So to produce a contact binary, people invoked, again, the gas drag. The big difference here being that these lobes are kind of like 10-kilometer size, not 100-kilometer size like the observed wide binaries in the Kuiper Belt. Those large binaries don't care about gas drag. They will form and remain detached. But this small one, 10-kilometer in size, will be more exposed to the gas drag effects. So maybe over time, these two components would inspiral on each other, would feel the aerodynamic gas drag and would inspiral to get into contact. And that's the stage 3 that people have invoked for the formation of the contact binary. This has been studied to some detail using simple simulation. In this specific study, people ask what kind of collision speeds and collision angles you can have between the two components to preserve the narrow neck between them. Of course, if you smash them together, there will be debris and you will not produce a contact binary. So here in this work, people sample different speeds, different angles to ask what would work and what would not work. So this is a case that works. It's a case where the impact speed is of the order of meter per second, very low impact speed. For comparison, the speeds in the Kuiper Belt, the collisional speeds today, are kind of kilometers per second. But you need meter per second to produce something like that. right? So meter per second, and the second condition was you cannot smash them with zero angle. The collision have to be tangential even. If you would have like on-center collision, you would need much, much, much lower speeds. So this is consistent with Arrokoth being a detached binary to start with that inspired slowly, and then during the touchdown, the speed was extremely low, and the speed vector was tangential. This is also consistent with the current rotation of Arrokoth. The rotation or the spin period is about 16 hours. And it turns out, if you assume low densities of these components, that 16 hours is also a Keplerian period when just before these two components touched. So there is an independent check on this possibility that Arrokoth was a detached binary before the contact. So this is the model on the left side and the real body on the right side. And you can see that the neck is about the same. These are some of the failed models. If you assume that the velocity is still only 10 meters per second, it's tiny, you just destroy the large lobe. And if you assume that the velocity is 5 meters per second and the angle is 45, you can produce contact binary, but the neck is much thicker than the observed one. And in this case, you get the right result. So this is an interesting study, again pointing to binary formation. So so that's for the contact binary. How about the flatness and the mounts, which were the two characteristics I mentioned? Now, this is more of a speculation at this point than a conclusion. But, well, if you have a simple collapse of a pebble cloud, these pebbles collide and then they collapse into a body, then obviously the surface of the body would be smooth. You wouldn't have any mounts because of the pebbles are millimeter, centimeter. They would just arrange on an equipotential surface and you wouldn't have mounts. But it is also possible that during the cloud collapse, there was a gravitational fragmentation. Unfortunately, the existing simulation of the collapse, they don't have enough resolution to show this. But it's potentially possible that there was some genes instability or something that produced these components, and it will need, future simulation to understand whether it is possible. This stage at this moment is difficult to study, but it potentially is possible. So if you would form these 5-kilometer bodies in the first place, then you can ask the question when they come together, could they produce something that looks like the large lobe with the mounts and the... So that's a question we can address. So this was done before. Basically, it was assumed that the 5-kilometer lobes form. There are about 30 of them, and they were given properties of a gravel. So this code is capable of accounting for real material properties of the components. People tested different speeds of random speeds. Again, you can intuitively understand it. If the speeds are too large, you will smash things together and nothing survives and will be kind of like a smooth potato on the surface with no mounts. And of course, you want to give it some global rotation because if you know that the large lobe is an oblate spheroid. So to produce that, you need some rotation, right? So this is one of the simulations that worked quite nicely. You can see the components coming together, squeezing each other, and producing something that actually looks like the large lobe. It has a 2-to-1 axial ratio, which is the measured axial ratio for Venno. And you can see that some of the mounts kind of survive. Of course, if the velocities would be larger, then you would produce a smoother surface. So here's the model on the left, the observations on the right. And there are certain similarities between these two. There are also differences. For example, this large mound is actually the largest mound on observed Venus is in the middle. But if you look here, you have like 3 small mounds, or maybe 4 small mounds in the middle. That may be related to the simplification of the simulation that you have equal size components, exactly equal size. In fact, you would have like different sizes, right? Maybe 3 kilometers, 4 kilometers, 5 kilometers, 6 kilometers, 7 kilometers, like range of sizes. And in that situation, maybe you could get the largest lobe or largest component in the middle, right? Potentially. But as I said, this is more of a speculation than real results. The Arrokoth is the only object we have seen from close by in the Kuiper Belt. But in the model, you can play with the rotation. You can assume the rotation was faster. Maybe some clouds of pebbles rotated faster, or maybe some clouds rotated slower. And of course, intuitively, that gives you what you expect. Sometimes you get more oblate body, sometimes you get more spherical body. So not necessarily everything in the Kuiper Belt should look like Arrokoth, right? You can have more spherical or more oblate bodies, and you can have all sorts of contact binaries as well. So this is some of the points that you may want to remember from this lecture. The streaming instability and gravitational collapse is capable of making equal-sized binaries with preferentially prograde orbit, which fits very nicely observations. You expect wide separation, correlated colors, and all this matches observations of Kuiper Belt binaries, and that in fact represents a strong evidence for planetesimal formation by the streaming instability and gravitational collapse. And given that the streaming instability is not too sensitive to conditions in a protoplanetary disk, it's likely that it happened elsewhere in the solar system, in the asteroid belt, in the terrestrial planet region, in the giant planet region, and probably also elsewhere in galaxy, which is relevant for exoplanets. And well, that's why we have planets, including the Earth. And in addition to that, the streaming instability triggered collapse could potentially, although there are lots of speculation involved in that, explain Arrokoth. The fact that it's a contact binary, has flattened lobes. I didn't talk much about aligned rotation, but it could potentially explain the mounds. So this is the end of this lecture. I just wanted to remind you, in case you are interested, come next Thursday, 10:30. And we will talk about the early evolution of the solar system, formation of comet reservoirs, and I will also explain how the present-day comets evolve from these reservoirs close to the sun, where they become active and produce comet activity. Thank you.